Next Tuesday in lab, you'll submit the report for Lab 10. And I've just collected homework 5B from you. The next homework assignment, covering some questions in Chapter 6, is due on Thursday the 14th. So that's a week from today. That problem set, oh, there's some overlap there. Another misprint, right? Okay, so cross those out. I apologize for that. As you can tell, I was in a bit of a rush today. I had some student questions that here we go. We'll get it right. There it is. Now I think that's the way it ought to be. All right. So problems 7, 11, 21, and 28 are due on Thursday, and then 41, 55, and 62 will be due the following Tuesday. Ordinarily, I have that whole assignment, all of Chapter 6 at once, and I just thought it would probably be easier and more manageable if I broke it up into pieces. Problems 7 and 11 are covering jets, and 21 and 28 are covering veins, and then not the veins in your body, veins. We'll talk about veins, what they are. And then on Tuesday the 19th, problems 41, 55, and 62 are covering pipes. And this is all having to do with different types of momentum problems. So let's cut into pieces now. And then we're going to have the exam on Tuesday the 19th. That's the Tuesday the week before Thanksgiving. So I guess that's 9 days before Thanksgiving. That Tuesday we'll have the exam during lab time. And in class, we'll do like a lab exercise having to do with WaterCAD. The homework assignment you've got due that Tuesday, so homework 6B, will be due at our normal 11 o'clock meeting time. And then the 2 p.m. time that we get together is when we'll have the exam. Yes? Yes, it is. And so if you want to check your answers, or if you have any uncertainty about what you've learned in that homework 6B, feel free to stop by my office, and I'll be happy to tell you if you've done the problems right. I don't want you to feel like, you know, there's any suspense there. I'm not sure if you've understood the concepts. I want you to get a chance to have it all ironed out. So. Probably not. The grader's fast, but I don't think he's that fast. I bet he'd have it done by Monday, though. Other questions? Okay. Well, we're in Chapter 6 now, Momentum. And to get the flavor of where we're headed, I thought we'd watch a YouTube video. We just do a lot of that in here, don't we? This is a pretty good one. This is one of my favorites. I've been showing this video for a long time because it's a good one.
Ei ihan kevyt olekaan. 3 kiloa kappale painaa kenkä. Siinä on kaikki polttoaineet. Oletko sä kokeillut lenkillä? Lisääkö juoksutehoa?
Tuolta sit niinku hönkää.
Lisa?
No?
What are you gonna do with us?
Fly. I like flying.
Forrest Gump, I guess. That's jet fuel.
It's here. Okay.
Love the helmet. Hyvä. Meillä on toi...
This is Finland. Very rough country.
No.
I just said that this kind of weather, if you land on the water, you're gonna die.
Tuutte jäille. Johnny?
Hey. I was fucking first one to do it. I jumped from 2,200 meters and flight until the gas tanks were empty and all pulled 1.5, and I was able to maintain the flight level in 2,000 like a half a minute.
All right. Well, we're going to talk about some of the technical details of that a little bit later today with an example, but essentially it's got it all there as far as fluid mechanics are concerned. We've got Bernoulli's equation giving him lift. We'll be talking about momentum, which explains how he's able to derive thrust from the liquid jet fuel. It's a pretty interesting video, and for me the sad thing is that there just aren't more of them. I mean, he's done a lot more of those jumps, but he just must be sort of a low-key guy because he's not posting selfies of himself, you know, doing his jet flights. There's very few videos. I guess he's not a publicity hound. He just likes flying more than being famous because it's pretty awesome stuff that he's doing. Some specifications. Each one of those boots gives 12 kilograms of thrust, and the 16, right, I can read. Thank you for 16 kilograms of thrust per boot, and the actual jet engines, those are engines that are meant for like hobby aircraft. You know, people have these remote control planes, and each one of those came from a kit meant for a remote control plane. He starts it up with a mixture of butane and propane, and then it actually runs on jet fuel grade kerosene. And the burn rate is half a liter per minute for each jet. And so theoretically, each one of those bladders that he had, you know, looked like maybe a hot water bottle. I think each one of those was carrying about a liter of jet fuel. So theoretically, he should have around 2 minutes per jet. And that jump that they showed was that we watched. He jumped from 7,000 feet. And ordinarily with those wingsuits, the glide ratio is maybe you can get 3 feet horizontal. No, maybe I've got it backwards. It's a 3-to-1 glide ratio, meaning I think that you'll get 1 foot of forward motion for every 3 feet of descent. And what he was trying to do is basically shatter that and actually try and maintain horizontal flight. And as he says there in broken English, he's a Finnish guy. He was able to fly level at 2,000 meters, but when he started to try and climb, that he stalled. And subsequent flights, reading a little bit about more, that was the first one he ever did. He has been able to actually climb and gain altitude, but there aren't videos for those. So what we're going to do is a little bit later talk about that case in terms of momentum, fluid momentum. The jets is what was powering him, and we'll be looking at jets as one of the 3 main problem types that we cover in Chapter 6. Momentum, the equations that we use in fluid mechanics for solving momentum problems are derived from Newton's second law. Newton's second law says that an imbalance in forces applied to an object with a certain mass m will cause that object to be accelerated at the acceleration rate a. And so if you have some object at rest, then you can overcome its stationary condition by applying an imbalanced force. Now, what we do in momentum is we substitute the definition of local acceleration in place of the A in Newton's second law. And remember, from our earlier discussions in Chapter 4, we've talked about a couple of different kinds of acceleration. There's centripetal acceleration, or rotational acceleration, in other words, and that was the U-tubes that were rotating around in circles and caused the liquid level to change, or in some cases the pressure to change in the fluid. We're not talking about rotational acceleration here, and neither are we talking about convective acceleration. Convective acceleration was that velocity is changing as a function of position. And it's convective acceleration, for example, that is behind Bernoulli's equation. So what we're talking about today is neither of those, but this is the local acceleration. So velocity changing with respect to time. If we make that substitution and we have v divided by dt, that was the acceleration, and we had some mass of particles, we can now think about a system of particles. Instead of just one solid object, m times v can be replaced by us talking about a system of particles. And in the Reynolds transport theorem back in chapter 5, the idea of a system being a continuously connected grouping of particles, that they can change shape and they can change location, but they're connected. What we can say is that if you have an imbalance in force, you can change the momentum of a system of particles over time. This is how we'd express it by substituting it back into the Reynolds transport theorem. Remember that the two terms of the Reynolds transport theorem are storage and transport. The first term here, where we're talking about a control volume, we keep track of accumulation of some property, some intensive property inside of a control volume. And so that property should be related to mass, and here it is related to mass because we're talking about a jet, for example, that has velocity. So the lowercase v here is referring to velocity, and this is a fluid that has a certain density, and dv, where the v with the strike through it is referring to volume. We're talking about trying to find out how much the particles accumulate inside of the control volume. So we can balance our understanding of how the system's momentum is changing over time by saying how much momentum is accumulating inside of a control volume, and then, more importantly, for most of the problems we solve, is the second term in Reynolds transport theorem. This second term is the transport term. It's the movement of mass across the control surfaces. CS stands for control surfaces. And so if we examine that term more closely, we again have the velocity of a fluid, whether it's a gas or a liquid. We'll solve problems with both. There's the velocity of the fluid, its density, again the velocity, and so those are both velocity terms there. And then dA is the incremental cross-sectional area that the fluid is traveling through. Now V is in there twice because when we have V times dA, that's essentially a volumetric flow rate. Remember, if A is the cross-sectional area, V is the velocity, then Q equals VA. So as we'll see here in a minute, the applied version of the momentum equation that we use, normally we say it's very rare that momentum will accumulate inside of a control volume. You can't really store momentum very easily. You kind of can. And one case that momentum is stored is in regenerative braking on some hybrid vehicles. You know, like a Toyota Prius, for example, when it's slowing down, it converts that energy that's being lost into electricity that goes into the battery. Some other hybrid vehicles, instead of converting it to electricity, they'll start spinning a flywheel so that when you're braking, what the car is doing, rather than converting that power into electricity, in some hybrids, when you're braking, you're starting to speed up a very heavy disc. And so that disc is spinning. You're sitting stationary at a stoplight. There's a disc spinning that has a lot of mass to it. And then when it's time to accelerate, you can harness the power of that spinning flywheel to give you some of the power you need to accelerate. So that's another way. That's a way that momentum is sometimes stored, but those are awfully rare. And so ordinarily what we do is we say that the sum of the forces that are applied to a system, the unbalanced sum of forces applied to a system, will be equal to the momentum that's accumulated and the flow of momentum through the control surfaces. This is still pretty abstract. We have a more applied version of the equation that we'll use. And so this is the statement that's saying, let's assume, yeah. Yeah. Yeah, we'll have momentum problems where you're given the flow rate, and maybe you'll be asked to calculate what's the force required to hold the system steady. That might be something that you'll see. Like I was saying, it's pretty rare for us to have momentum accumulation. And so in the Reynolds transport theorem, we'll oftentimes neglect or set equal to zero the idea of momentum accumulation. And when we do zero momentum accumulation, it allows us to say that an imbalanced sum of forces will be what causes a difference between the flow in and the flow out through control surfaces. And so let's speak in more concrete terms now here. Let's say we've got a wedge, and there's a jet of water that's going to intercept this wedge. You'll expect some of the water to fly off that way, some of the water to fly off that way. Just think about if you were holding that wedge in your hand, and the jet of water is traveling from left to right. What way are you going to have to push on that wedge to hold it steady? You're going to push this way. So I'm going to have to apply an external force to hold the system steady. So what we're saying with the Reynolds transport theorem is take some object of interest, enclose it with a control volume. Now, these outside boundaries of the control volume are our control surfaces. Let's keep track of the flow of momentum in and out of our control surfaces. And so here we've got flow in. This is our in through the control surfaces. This is our out. This is one of the outs. Here's another out. In the Reynolds transport theorem, what we're saying is you can find out how much of a force has to be applied, how hard you have to push to hold the system steady, by considering velocity, the density of the fluid, velocity again. We'll combine these terms together where we can. And then the incremental area. So if you look at in versus out, what we're going to be doing is an accounting of how has the velocity changed. And remember that velocity isn't a scalar, it's a vector. What that means is that we need to keep track of not only its magnitude but also its direction. And so here it may have a certain speed. It may be going 18 meters per second. And maybe it slowed down a little bit when it came into contact with that wedge, but maybe it didn't slow down. Maybe it still has the same velocity. But what definitely changed was the direction component of that jet of liquid. And so when we're working problems like this, what will our strategy be to find out how hard do we have to push to hold the system steady? We'll basically be looking at how did the velocity change. And how much the velocity changed, either in magnitude or direction, accounts for the force that has to be applied. That's where we're headed. Now, there's different kinds of forces. Body forces, as is described in your textbook, can be thought of as gravitational forces, electrostatic, or magnetic. Those are forces that can act on mass without necessarily needing to have any physical contact. And so you've probably played with magnets before and know that you don't actually have to have two magnets touch each other before you can feel the force, the repulsive forces or the attractive forces. And the same thing is true of electrostatic forces. If you rub your head on a balloon, you know that old trick, and then you can sort of feel a little something when you put the two balloons together, or if you get it to stick onto the wall. Those electrostatic forces don't necessarily have to have physical contact before an object can be accelerated because of the forces. And electrostatic forces are used a lot in air quality. If you have an industrial process that's generating very fine, small particles like a dust, if you have a factory that's in the smoke has dust particles, then one of the things they'll sometimes do is they'll send the smoke through plates that are charged. They'll have a series of positively charged plates. You know, they'll just essentially connect an electrode to a metal plate, and they'll send air through it. And if the air has dust particles, then the dust will be attracted to those plates. And so the plates don't have to be touching the entire surface of the air, but simply those dust particles have a negative charge on their surface, and they move towards the electrostatic precipitator, as they're called. So those are a few examples of body forces, the forces that don't necessarily have to have contact. But in momentum, the forces that we're going to be calculating, the imbalanced forces required to hold the system steady, are surface forces that do have a physical contact. So other examples of surface forces will be the hydrostatic force of water acting on a dam, or the buoyant forces of water pushing upward on a boat. Here it is. This is the equation that you're going to apply a lot of times. Now, here I've put in x just as an example, but you can apply the same form of this equation in the y direction, in the z direction. You just substitute y or z any place you see the variable x there. The way to interpret it is as this. Here we've got a control surface. What we want to do is look at the flow of momentum out of the control surface minus the flow of momentum in the control surface. And so this equation answers the following question. What is the force required to hold the system steady? Direction is really important. You know how we have sign conventions? We assume that to the right in the x direction is positive. So this is the positive x direction to the right. We're going to assume that the English language translation of this formula is what force is required to hold the system steady. So in the example that I drew earlier, a wedge that is deflecting the stream of a jet, we know that we're going to have to push to the left to hold the system steady. Let's think about that in conceptual terms here. How does that fit into this equation? Okay, let's assume that velocity in, so the magnitude of the velocity in is equal to the magnitude of the velocity out. So let's just assign it a number for convenience sake. Let's say that the V in is 10 meters per second. So that's the velocity of the jet that goes in, and the V out is also 10 meters per second. So this is a really smooth surface that didn't slow down the magnitude of the jet at all. It goes in at the same velocity that it goes out. The mass flow rate in and the mass flow rate out. So m dot stands for mass flow rate. And remember that mass flow rate is equal to the density times the volumetric flow rate. And continuity tells us that the mass flow rate in has to equal the mass flow rate out when there's no accumulation. And in this little drawing on the board, there isn't like a storage tank that's progressively filling. It's just there's a jet that's getting split. And inside of this control volume, there's no accumulation of mass. And so the mass flow rate in equals the mass flow rate out. And so maybe what we're talking about, just to plug in some numbers, maybe we're talking about 10 kilograms per second. So the velocity in was 10 meters per second. The velocity out, now the magnitude of the velocity out is 10 meters per second, but let's say that it's deflecting at an angle of 45 degrees. You know, as the jet came in, all of the velocity was in the x direction. Now, the jet that's going out, the component of velocity in the x direction is 0.707. You know, we have the sine of 45, the cosine of 45, and so we can find out what is the x component of the velocity and what's the y component of the velocity. So this will be the velocity in terms of x. This would be the velocity in terms of y. So in this equation, what it's saying is that the force required to hold the system steady is going to be out minus in. So what force do we have to apply? The mass flow rates are the same. Mass flow rate in equals mass flow rate out. And so that's going to be a common term. So it's just going to be mass flow rate, and then we're going to have the velocity out minus the velocity in. Velocity in was 10 meters per second. Velocity out is going to be in the x direction. Velocity out in x, velocity in x was 7.07 meters per second. And here's another thing. They're both going in the positive x direction. We should always put a negative number for the velocity if it's going to the left. But in this example, both the in and the out were in the positive x direction. So we have positive 7.07 meters per second and positive 10 meters per second, but we're subtracting the flow in from the flow out. The mass flow rate was 10 kilograms per second. So the force required to hold the system steady is going to be 2.93 times 10, so it'll be 29.3 kilogram meter per second squared. Now what do those units end up to be? That's a newton. A kilogram accelerated at a rate of 1 meter per second squared is a newton. So that's 29.3 newtons is the force that's required to hold the system steady. But one thing to point out is that there was a negative sign there. So it's negative 29.3 because 7.07 minus 10. And so what does that mean? The sign of that being negative, it means that the force required to hold the system steady is to the left. So we had assumed that the positive x direction is to the right, and so we can know how hard we have to push on that wedge to hold the system steady. So is that making sense so far? Any questions? Yeah. So you're saying, like, what if this jet wasn't canceling it out? What if it all went at an angle like that? If it did that, then yes, we'd also have to push down on this to hold it steady, right? Or let's see, no, we'd have to push up. We'd be pushing up. So there would be a y component there. So we could apply it in the y direction. So just to simplify things, I said, well, let's assume it's being split evenly so that there's no y forces in this instance. Well, let me ask you a question. What if instead of a 45-degree angle, how would the magnitude of the force change? Would the force be greater or less if this wedge was like this and it was completely changing direction like that? Why is it going to be a greater force to hold the system steady? All right, so looking at the equation, there would be no velocity out in the x direction. There would only be velocity in the x direction. So like this is fully vertical, so there is no velocity in y. What if, just to take this even further, that's not the maximum force, by the way. What if we had a wedge that was shaped like this? All right, and what this wedge does is it totally makes the jet do a 180, like we're at a water park or something. So it comes in and it changes direction completely. Now what's going to happen? The force is going to be double, right? It's going to be even more because now velocity out, we do have velocity out, but it's in the negative direction, and the velocity in, so it's going to be like negative 10 minus 10, and so it would be effectively 20 meters per second multiplied by the mass flow rate. So that gives you an idea of one of the concepts here, but really what I want to emphasize right now is the English language translation of this equation, and that is the force required to hold the system steady. Because sometimes, just to trick you and try and get you to make a mistake, so I can say, gotcha, I'll ask you the opposite of that. I'll say, what is the force that the jet applies to the wedge? That would be the opposite of what this equation solves for. The equation solves for what force do you have to apply to the wedge to hold it steady? Well, what if I said, what is the force of the jet on the wedge? Then you'd solve this equation and forget the English language translation, and then I'd get you. But I don't actually want to get you. I want you to have all the problems get right. I don't get point. I used to think when I was a student that, man, the professors must have to pay for the points that they give out to students. They're so stingy with them. Why don't they just give everybody good grades? Why do they got to ration these grades out? I don't have to pay for the grades I give you. I don't. You earn the grades. That's what it is. I'm not giving them to you. You earn them. So I'm not trying to make you trip up, but I want to get you ready for the real world, and there's a lot more stumbling blocks there than you'll ever see at Marshall. So you can apply that at the y direction just as easily as you can apply it in the x direction. Now, sign convention, as I've pointed out a couple times already, is going to be really important. So remember that what we need to do is assume that to the right is positive x, up is positive y, and that applies in interpreting the magnitude of the velocity. Now, mass flow rate is a scalar. It's not a vector. So mass flow rate won't have positive and negative. It's just an absolute quantity. But the velocities do have direction. Now, here's another thing, is that we have to sometimes think a little bit about what is in and what is out of our control surface. Sometimes the tricky part of the problem is really just knowing where to draw the system boundaries. So let's step through a couple of examples of that. This is obvious here, right? That the velocity in will be positive, sign convention, and the velocity out will be positive here as well. So it's out minus in, and both of them are to the right, which is positive. Okay, now what about this? All right, we've got out only has y. There is no x component of the velocity stream that's going out. And the velocity stream that's going in at 1 is to the right, so we'd put a positive value here. But in the second case, this stream that's entering the control surface from right to left, that's going against our sign convention, so we need to put a negative sign in whatever velocity we substitute in there. And so it's going to be minus the whole term, but then on top of that, the v value itself would have a negative number associated with it. So the two negative signs may cancel each other out. And what about this one? All right, dissect it. The same way that I've dissected it here, in your notes there, dissect each of the streams, their y component and their x component, which is positive and which is negative. All right, so stream 1 is an in, and its velocity in the x direction is positive. The component of its velocity in the y direction is negative since it's down. Stream 2 is also an in. Its velocity component in x is negative since it's to the left, and down is negative because it's down. Stream 3 is an out stream, and it is positive in the x direction and positive in the y direction. So pretty straightforward, but then we'll get to some of the problems in the homework assignment, and we'll need to be very vigilant that we keep track of what is an in, what is an out, and then also whether it is positive or negative with respect to its sign convention. Any questions about this topic? It's going to be really important. So here's the approach we'll use to solve problems. We'll go through these steps. We'll first of all select the control volume. We'll try and decide what is our object of interest that we're trying to analyze. And so is it a wedge that's changing the velocity of a jet stream? Is what we're interested in a guy with a jet boot pack and a wingsuit? We'll enclose our system of interest with the control volume, and then there are governing equations that apply. We may sometimes combine momentum with Bernoulli's equation. We may sometimes have to combine momentum principles with continuity equation in order to solve what are the mass flow rates and so on. We can draw sketches of the body forces and the surface forces, if there are any, and then look for momentum accumulation, which in most cases there won't be any, and then sketching the momentum flow just to get an idea of where is the jet going in and where is the jet going out. Yeah. What's that? I don't think so. All right, well, let's take a look at this example in a little bit more detail. Here's the jet engine. 16 kilograms of thrust per boot is the specification that I was able to find, and it's burning kerosene. I've given you the chemical formula for kerosene. I know engineers usually love chemistry. I saw some grimaces when I had the chemical formula there. I don't know why everybody hates chemistry so much. We're burning 5 liters per minute. That's the liquid burn rate of the fuel. And so let's try and find out what is the exit velocity of the gas that would be required to generate that much thrust. So in other words, you know, when he was sitting at the edge of the trailer and he was spinning up the engines just to test them, how fast was the exhaust of the jet coming out of his boot if it really is generating 16 kilograms of thrust? So what's the minimum exit gas velocity that can do that? So we'll work through this example together real quickly here. Let's first of all draw a sketch and say here is the jet boot, and what it's doing is that the fuel goes into the jet boot and there's air entering it, and then the exhaust comes out. All right, now the density of this fuel is 0.795 grams per cubic centimeter, and the chemical formula 2C12H26 plus 37 molecules of oxygen goes into 24 CO2 and 26 H2O. That's the balanced formula for it. The molecular weight is a ratio of 340 for the kerosene, 1184 for the oxygen, and that works out to a ratio of fuel to air ratio of 1 to 3.482. So that means that we're going to have 1 gram of kerosene for every 3.482 grams of oxygen. And the reason why we want to know that is we know how much fuel is going in. We'll be able to calculate the mass flow rate of fuel. We also want to know what's the mass flow rate of the air that's going in. All right. So regarding this fuel, there was 0.5 liters per minute of kerosene. That is 500 cubic centimeters per minute. of the kerosene. And if we multiply that by the density of the fuel, which is 0.795 grams per cubic centimeter, that means that essentially the fuel is being burned at a rate of 397.5 grams per minute. So the burn rate per second, that means that every second there is 0.006625 kilograms per second of kerosene. And we're doing this to define m dot, the mass flow rate. And based on the molecular weight ratio, then the oxygen that needs to be available for that combustion is 0.02307 kilograms per second. And that's oxygen. Okay. Now, 16 kilograms of thrust that is, if we consider in terms of W equals mg, that is 16 kilograms times 9.81 meters per second squared. That is 157.0 newtons of thrust. So what we're going to try and find out is for the force that it is applying to the foot, that's the force, and we've got a mass flow rate that we'll be able to define in terms of kilograms per second. Remember that oxygen is only about 20% of the air in the atmosphere, and so if we account for the fact that air is 0.02307 kilograms per second divided by 0.21. And so air is a mixture of both oxygen, nitrogen, and other gases, trace gases. And so if it's 21% by mass, the oxygen fraction relative to air, and that works out to 0.1099 kilograms per second. So we add that together with the fuel, the mass flow rate total, air plus fuel, the mass flow rate that's entering that boot is 0.1165 kilograms per second. So that's how much is available to also go out through the exhaust, because there isn't any accumulation of mass inside of that jet boot. It's all of the mass that comes in will also be exiting. So now we're going to set this up as the momentum part of the problem. Find out how much force is that boot actually, for the 16 kilograms of force that the boot's applying, and the mass flow rate that we know, what velocity of jet is required to accomplish that. So, you know, here's our boot, and it's shooting out a gas. And if we were going to hold that system steady, we would apply some force. So the force is equal to mass flow rate out times velocity out minus mass flow rate in times velocity in. In the problem statement it says what's the minimum exit gas velocity required to generate that thrust. And when he was sitting on the edge of the trailer, the gas that is entering the jet boot has a velocity of 0. Like if we say here is our system and the air is being like drawn in over here, right here at the boundary, the velocity of the entering gas is 0 as a minimum. When he's actually flying, probably the velocity that enters, the velocity of the gas entering the boot is higher, but let's assume that V in equals 0 at minimum. In other words, when the guy's sitting on the edge of the trailer. So what that does is that says that this whole term will cancel out if the velocity of the inlet gas is 0. And so the force will simply be equal to the mass flow rate out times the velocity out. And what we're trying to do is solve for the velocity out. That is the force divided by the mass flow rate out. And the mass flow rate is, the force is 16 kilograms, which we converted into 157 newtons, which is, remember, a newton is a kilogram meter per second squared. And we divide that by the mass flow rate, which we said was 0.1165 kilograms per second. And so the kilograms are going to cancel out. The seconds in the denominator will cancel out with these ones. And so we'll end up with a velocity of 1348 meters per second would be the velocity, the minimum exit gas velocity to generate that much thrust. Now, there's a lot of assumptions built into this example, but in order to generate a true 16 kilograms of thrust per boot, that's what would be required. And so the way that it works is if it was going to be less velocity, he'd have to increase the mass flow rate that's going through there. And that's why on a rocket motor, we'll have some problems where it shows the rocket motor tapering down to a nozzle like that. You know, there's a solid fuel that's burning and forming a gas, and the gas shoots out. They have it contract down to a really thin section because the higher the velocity is, the higher the thrust that can be achieved in terms of momentum. All right, we're out of time. We'll pick up more about momentum when we get together in class on Tuesday. Until then, what you should be working on would be the lab report that you have due in lab on Tuesday. And also, you can get started on homework 6A if you want to get an early start on that, since it'll be due a week from today.